after this is done. But this is like a one big package of machine learning and deep learning stuff. And this will be hands-on. We have a lot of time with us. We have 1 hour, 45 minutes for this part and 30 minutes for the deep dimensionality reduction. So I would highly recommend everyone takes part in this by actually executing the programs, because this is something similar to what you'll be anyway be doing with your own projects. So give me like an emoji if you now understand how to be on an interactive node or do submit a Slurm job on a GPU node. Yeah, Linus does. Yes, RT does. Arthur, yes. Oh, everyone does. Nice. So, well, we have only 5 people here today, so I'm gonna give you like first class citizen treatment with the machine learning, deep learning thing. So you can ask me your personal project questions as well, if we have time. So in today's this workshop with machine learning and deep learning, we'll be talking about 3 major libraries that everyone nowadays uses, which is scikit-learn, also called as sklearn, PyTorch, and TensorFlow. And give me another emoji if you use any one of these in your day-to-day, if these are like your day-to-day drivers. No one uses it? Does anyone has any experience with it or has like coded a little bit of it? Maybe not. Oh, no one has. Okay. All right. So this is very new to everyone. So this is exciting. This means, so in today we'll be going through like an overview of these libraries and we'll try to use them in our own respective HPCs. We'll also try to use GPU nodes if we can. I was trying it before this break, but there was, because of the limited number of GPU nodes, it's hard to get one. And we'll see some differences between these. What are these used for? How can you get started with them? I won't be like going through the code itself to explain what's going into the code. But if you have questions, I can take them. It's good to have like some general knowledge about statistical machine learning and somewhat about deep learning to understand the code, which are like given in the examples. But I can still like give like very overview of what it is and how to use them. So this is what I was mentioning, comparison. This is, I'll give you, then we'll talk about the tools that we have on each HPC cluster. And this is a table where you can see which modules to load for each of one of them. We'll proceed to scikit-learn. We'll go through some examples. We'll do exercise. Then we'll go PyTorch and TensorFlow hand to hand together. I mean, because people either use one of them at one time. So I thought we'll just tackle both of them together instead of going to them one by one. And we'll see some of their examples. I'll talk about some tips and tricks and my personal lessons learned from working with these libraries, and also by just looking at the code of other users and researchers at different HPCs, what the mistakes they do, what I do, and these are some common things that I found out. So stick to this part. This is quite useful. And then in the end, we'll finish up by doing some more exercises. And I'll just let you all code your own things and you can ask me questions related to that. So even though it's not mentioned here in the beginning, but what I'll request from all of you now is to get hold of an interactive node if you can, so that by the time we reach the exercises, you already have an interactive node with you. If it's a GPU node, it's even better. But if you can't get a GPU node, just get a CPU node, interactive node. We'll also submit some Slurm jobs. So we don't need interactive node for that. Of course, it'll be a submission. But it's better if you have an interactive node. We can also start a Jupyter server there. We can work with these IPy notebooks with that. And then I'll also ask you to like create some environment. So mm, this will start around like when we start reading about PyTorch and TensorFlow. And I have mentioned but hold on, let me just refresh this page. I have is it? Yeah. So under PyTorch and TensorFlow in the exercise section, you will see what environments to create. And you can start doing them right now. I'll give you like 5 to 10 minutes before we actually start doing something, so that by the time these things are done, when we reach to the exercise, everything is already set up. So for PyTorch TensorFlow, these are the two environments you would need. For PyTorch, this is Torch Vision, Jupyter. For TensorFlow, it's TensorFlow, the CUDA version of it, the Jupyter, scikit-learn, and Pandas. But of course, we'll also be looking at modules. And some exercises will require you to have these environments. So two things, get an interactive node and create these environments. You can create these environments without an interactive node as well, of course, because the storage is shared, right? So I'll wait for 2 to 5 minutes and let me know if you have any questions regarding these two, and then we'll start talking about we'll start with the first part, which is the comparison. I'm pausing here because I want everyone's attention when I'm doing the comparison and things. Meanwhile, you can start getting your interactive node and create environments.
I don't see why we need to create those environments when all those Python packages are available in the module, right?
Not everything will be available when you work on your own project, of course. And these ones which are mentioned here, yes, these are available. But then I want you to actually create these so that you understand how to use them when you're interactively working with your notebooks or the Jupyter server or the Python files. And like with time, as you know, that these libraries grow. So it's just easy to, if you now just get like used to creating environments as well. Not everything will be available in terms of modules, and like HPCs like PDC, NSC, they don't even have these modules. So NSC doesn't have them. They recommend that you create your own environment. PDC have few of them, but these are singularity containers. Um, so then it's a different way of doing it. I do not see anyone from PDC here though. Is there anyone from PDC? Maybe not. Yeah, so Linus, you're lucky that you have everything on Rakam. Can I get like some emoji that I know that you are actually working on these two tasks that I just gave? All right. Thank you. Yeah, Linus.
No, I meant to say I'm working.
Oh, okay.
Didn't
Got it.
find.
So there's like a React option called React, and that's where every emoji resides. Can I, so Andreas, are you from, which HPC are you from?
I'm from the Kebnekaise.
Okay. I was asking because I'm gonna take an example from Kebnekaise and run it on Kebnekaise, and then I'll run it on Tetralith,
Mhm.
one example. And I can also run it on Rackham or Snowy. Uh, what about Angela and Sarah?
Hi, sorry, I just arrived here. I don't know what you're doing. Sorry.
Okay. So the task was to get one interactive node so that we can work upon the exercises when we reach there. So get one of the interactive nodes, and in the PyTorch and TensorFlow section, uh, at the end of it, there is an exercise where I've mentioned like how to create environments. So also create these two environments on your HPC.
Okay, thank you.
How is it going, Arthur? Are you able to create environment?
I think so. It was taking quite a long time
Yeah,
for
it will
some
take a
reason.
long time. But okay, so you have asked for an interactive node and you have initiated at least the um, environment.
I was just creating the environment for now, which I think is okay, right? Separate, and then I can create the node after.
Yeah, like you can create one more, you can open up another terminal and ask for a interactive node there. Like how I do it usually is like, okay, first of all, I prefer VS Code, coding everything from VS Code. So you have like a terminal option here. You can click new terminal and you get a new terminal here after like SSHing. This is something I showed in the IDE day 2. And here you can like just create +1. So you can add more terminals here and you can do multiple things at a time. Or you can have a terminal like this one. And then you can have multiple terminals and work with that. How's it going, Sarah and Aarti? Are you also working?
Yeah, it's
Mhm.
I'm doing this pip install TensorFlow and CUDA, and it's happening. It's going.
Okay.
So yeah,
Okay.
it's going fine for me.
Yeah, same for me. I'm doing this pip install, these two options.
All right. So I guess I'll start now. You can keep running your pip installs in the side. It will keep running. And I'll start with this one. So let's begin. All right. So we'll start with the comparisons of these. Maybe I should make this bigger, like this. Yep. I hope it's big enough. So comparisons. We're talking about scikit-learn, PyTorch, and TensorFlow. First and foremost, scikit-learn is it's been there like almost the longest. It's been used for classical machine learning stuff, for like data mining things and clustering and classification and all that stuff. PyTorch and TensorFlow are deep learning libraries, and TensorFlow was one among the one which started by Google, was the first one. Soon PyTorch came into being. This was by Facebook, Meta. TensorFlow is so TensorFlow picked up pretty quickly in the industry because of that, because it came first and it was by Google. And it was picked up by industry, whereas PyTorch was picked up by academia because it's more manual and you can tweak things at a very basic level with that. Before TensorFlow, there were libraries called as Theanos and Keras. Theanos doesn't exist anymore because its work has been transformed into TensorFlow. Keras is the one which is still existing, but it's indirectly used in TensorFlow. So TensorFlow uses Keras in its backend. So when you're like reading the code, you will find these words like libraries. When you're using TensorFlow, it will say keras.dense something something, and that's because Keras used to exist before that, and so TensorFlow uses its backend to create deep learning models. Scikit-learn, on the other hand, is quite simple. It's quite like they have used, it's full of abstractions, and they have made it very clean to use for a user. And the functions are pretty neat to use. And it's just growing day by day. It's still growing. It's still improving. It's mostly used with serial models. That means if you want to do like parallelization with scikit-learn, it's possible with external libraries with it, but its main purpose is not for that. Whereas PyTorch or TensorFlow is like natively built to exploit GPUs. And deep learning application need to do that as well. So with PyTorch TensorFlow, you can play around with GPUs. With scikit-learn, you can, but it's not the one which is recommended for it. Just run simple machine learning, clustering, and such models with it. On your respective HPCs, you have modules that can load all these. UPPMAX has a module called Python ML packages, which has lots of machine learning packages in it, which includes scikit-learn as well. With HPC2N, we have for TensorFlow and for PyTorch, we have two different ones. And they are in their respective module names. And you'll also have to import module load OpenMPI and GCC with that. With LUNARC, something similar, you'll have to have a GCC with that, and it comes under TensorFlow and PyTorch. For NSC, you'll have to create your own virtual environment. With PDC, you are given singularity containers, and you'll have to call those singularity containers into your bash script in order to use TensorFlow or PyTorch. For future references, if you want to like start with these three things, I have given some links here in learning material. PyTorch, TensorFlow, scikit-learn, and some examples on how to do understand machine learning. For more advanced things like parallelization with these three things, I've given some links as well. You can read about them. But this is not covered today. Regarding the modules that are available, as I was saying, these are not the only modules, of course. There are many more which are available in all the HPCs. And most important being NumPy, SciPy, scikit-learn, matplotlib. So you'll find them almost everywhere except NSC. Piano doesn't exist anymore, and that's why except HPC2, and you won't find that anywhere else. That too for older Python versions. TensorFlow and PyTorch. Well, with TensorFlow, of course, Keras also exists because that's the backend. With PyTorch, you have, yes, you have in every other HPCs, you have these modules and you can look them up. Pandas, of course, is also available in all of them. In Python module, you can get the pandas. With SciPy bundle, you can get pandas on HPC2 and in LUNARC. And in Cray Python, you have FBDC. Beautiful Soup is usually for scraping internet and going through HTML documents. But you still have them available. Seaborn with matplotlib is used a lot. That's also available. Horovod is a parallelization library for your models, machine learning models. We're not covering Horovod here, and it's also not available anywhere except HPC2. Similarly, Ray is also another library which is also available. So if maybe you are at Alvis, you might use it. I've given a link here about Ray clustering for hyperparameter tuning. So maybe you can read them here. All right, so starting with scikit-learn first. As I was mentioning, scikit-learn is for classical machine learning things. We use it for data mining or clustering, classification, and all that stuff. Very heavily used when this data science wave came in industry. Most of them were just using scikit-learn straightforwardly. Along with it, there are other libraries, of course, which would go very hand in hand with scikit-learn. And good thing about scikit-learn is so mature that even PyTorch and TensorFlow uses scikit-learn sometimes to, for example, to do pre-processing of their data. So it's quite mature library and it's quite intuitive to use. Nice documentation as well. There are three examples that I might go through, but before that, I'm just going to give you an overview of what's in scikit-learn. And you'll find these classes or those components. It's called estimators, transformers, pipelines, datasets. For model evaluation, you'll find something. And parameter searches, you'll find something. Can I get like a reaction on if you have developed or coded or done anything related to machine learning? No? No one has? I also give it like a cross so that I understand you haven't. Okay. All right. So with machine learning, a very common pipeline I'm explaining here is you have your data and you need to do, let's say, predictions on an unseen data in the future, which might come in. So in order to train a model, and this is a very classic pipeline, by the way, you take the data you try to understand the data. And in that process, which is also called exploratory data analysis, EDA, you transform the data in a way that a model can make sense of it. And the process of converting the raw data into what model can ingest, it's basically called pre-processing the data. But you might hear words like feature engineering or data augmentation, things like that, which basically means the features, the data basically features, right, are somehow transformed in a way that the model can understand. And then the model is trained on this transformed data. And then the model spits out a prediction given a new set of data. And this new set of data is called test data, which is like an unseen data set, which the model has never seen. And that's how you test the model, whether the model is doing well or not, because now you have a prediction on that unseen data. And now you can see, okay, this is working well. If it's not working well, you want to improve the model. This is where something called as hyperparameter tuning comes in. So you're tuning in the parameters of the model so that you optimize the model. It's also called optimization, of course. And these same lingos are used in machine learning, also in deep learning. And it's like the words are twisted here and there, but majorly this is some sort of a pipeline which goes through. So scikit-learn as a library gives all the functions to do all of these steps. What are estimators? Estimators are those models that will understand your data. And these are the core objects of your scikit-learn. Things like to do linear regression. There's a linear regression class for k nearest neighbor classification. There is this class, decision tree. This is this class. There is another class, k-means clustering. There's so many models out there. Which ones to use, which ones not to use is a different talk altogether. But usually you'll see that you want to predict something, you want to classify something, or you want to generate something. And that's why generation nowadays is all AI, Gen AI is there. So these are the estimators when it comes to scikit-learn, it's called estimators. Transformers are the ones which transform the data. And this is not the transformers that you hear nowadays with LLMs, language models. These are not those transformers. So these came first, those came later. These transformers in scikit-learn's lingo means something which transforms the data so that the model can ingest and understand. And these transformers are, for example, scaling to do the scaling of these features or the data set, PCA, which we'll be learning about in the next section, for dimensionality reduction, TF-IDF, which is term frequency, inverse document frequency. This is common NLP, natural language processing thing. Not done much anymore, but it was quite common like 20 years ago. So transformers. And there's like a common function in transformers called fit and transform. Fit and transform is something you'll hear again when we look at the examples. Fit means fit the model. Transform means now transform the data. So it's like broken down. And I might touch upon why it's broken down in the future. Pipelines is a neat way of like arranging all these components of machine learning into like one nice package. So as the name goes, you might have like for pre-processing, you have standard scalar like we used for transform, linear regression, which was coming from estimator. You create a pipeline. You just say, okay, the first thing you'll do is scale it. Second thing we'll do is throw them into the model. It's called a pipeline, simple as that. So it like pipelines the whole machine learning system for you very nicely. Data sets, these are readily available, very common, famous data sets to play around with your machine learning models and test your models. So this comes under the class of data sets. And model evaluation is a set of functions you use to evaluate how good your model is doing. If it predicts how well it predicted. So things like finding the accuracy score is some of the matrices that you might use to evaluate your model. There are so many other matrices that you might use depending on your use case. And finally, to improve upon your model, you need some ways. And for that, the functions available is these parameter searches. Parameters being the parameters of the model, you would want to like tune in and find out, okay, this parameter set of parameters are the best combination. And this comes under something called as parameter searches. For example, grid search CV. Grid search is basically like a table of parameters and it plugs in all the parameters with permutation combinations and sees, okay, this is the best combination of parameters that works best for your model. So this was a brief overview of the components available in scikit-learn. I'm giving 3 examples here. First is with the model called linear regression. Second one is k nearest neighbors, and third is this decision tree. In machine learning nowadays, like most of the work can be just done by using decision trees because these are like excellent ways to find classes and group them as well. So decision trees are the best ones, which are like just used randomly everywhere. The next step from decision trees is called something called as random forests. They are like the collection of trees is a forest, of course. So that's why if you have a collection of decision tree, it's called a random forest. Okay, so hopefully I have the node with me still. And let's see. Okay. I will first module load everything here. I'm just going to copy everything from my own scripts and start. Meanwhile, if anyone has question, let me know.
With environments set up, the next step is to start Jupyter Lab on the compute node or GPU node.
Yeah,
Is that correct?
yes, you can start the Jupyter Lab notebook, and you can even because that's like those environments are for PyTorch at TensorFlow, I think, and we'll come there when we start PyTorch at TensorFlow. But we also have scikit-learn in the TensorFlow environment. So if you have TensorFlow environment ready, you can run these examples because the ones which we're talking about here are scikit-learn and matplotlib, and matplotlib is also available in, it's not available here, but maybe you can also do a pip install matplotlib in order to run these examples. But this is just me showing you examples. You don't have to run these examples. you'll have to do this exercise, and this exercise requires you to run modules so that you understand how to use modules as well. So it's up to you if you want to run your environments, that's fine with me. But otherwise, you can just look at it and run this exercise with the modules. I have another question. Oh, all right. So I am on HPC2N. I need my scikit-learn. So I am loading scikit-learn. For that, also load these. PCC. Oh. Okay, 0. Need 4, 9, 3.3. Let's try some. Okay. And then the lab. Let's check if I have. Is it even visible what I'm doing here? Is it big enough?
I can see it.
Increase it just a tad.
Yeah. Okay.
That's good.
Okay.
Likes to me.
So I was just loading the modules, which is scikit-learn, Jupyter Lab, and Python with GCC. And then I'm just starting the Jupyter Lab. Just note this is starting on my login node, by the way, because these examples are just very tiny. But in the future, the next exercises will have to be on a compute node or interactive node, as I asked you to log in. I open the picture. So we have the scikit-learn available here. Another step that I forgot to mention before we started these, like the session, was to also get your exercise folder again. Because I made a small change into a TensorFlow code. So do wget of your go to tarball exercises and just do wget so that you get the new exercises again, and then untar them. If you have been like working with your exercises already and you don't want to like make changes or remove the old exercise folder, you can create another folder. Let's call it day 4, or let's just call it machine learning something, and then do wget inside that folder so that you have the fresh exercises. But otherwise, we can see that we have a Jupyter server running, and I can see the server running here. And did I not answer? I also need matplotlib for the first one. I'm just going to stop the server for now. Matplotlib, and then start the server again. This is what happens if you don't close your Jupyter servers properly. Okay, so I'm going to fetch this link again and run this again. This time Matplotlib should work. Yes. So this is a linear regression one example, and this is a simple X and Y, which X is the input data, Y is the labels for these data. And what I'm trying to do is trying to learn a linear regression model by throwing in the X, which is the data inside the model, and using Y as a predictor for that. So if you remember, I was talking about fit method in scikit-learn, which is to do just that. So you can call model.fit, which fits your input into the and try to understand what the different parameters, so that it gets the Y, which is the labels, correctly. And once model understands which parameters are the best models, you can use the model to predict for some other data. In this case, I'm just predicting it for the same input data. Doesn't make sense, but you can just for example's sake. And then I'm just plotting X and Y and the line. This is the decision boundary. This decides, okay, this is a different class, this is a different class. So this is an example of simple linear regression model. Another one is this K nearest neighbor models. And this is simple again because I'm not showing anything here. I'm loading iris dataset, and iris is a class of flowers like these, and they have a distinction where their petals and sepals, the counts and the width and the length are different. And this is the data set here. It's a very common hello world sort of machine learning data set. So data sets is the class which we can use to load the data set for different like machine learning examples. I did load iris here. So you can check the data and the targets. Targets are the predictions, whether this is this kind of flower, this kind of flower, or this kind of flower. There are 3 kinds. And the input features are basically the petals and the sepals and the length and the width and the height and everything. So you see that here you have loaded the X and Y, X the input, Y the predictions, and then you split these into X and Y. This is another common thing to do in machine learning, where you have to, of course, split your data set. One part of it will go into just training the model. One part will go into will be unseen by the model, so that when you're doing your predictions later on, you can test those onto that set. So you should not learn your model on those held out test set. So this is what is used. It's called train test split is a common function again. It splits it based on, for example, 30% of the data should go into test size and the 70% will go into the train size. Then here I'm using K nearest neighbor classifier, which classifies into 3 classes because we want 3 classes of images here, flowers. And then again, you call the fit, you call the predict, and you check the score, and voila, we are 100% accurate. Wow, amazing. And The last example is of a decision tree. And as you see, like without going through the code, it looks like a tree. These are the leaves of the tree, and these are the nodes. You do similar stuff. You load the data set, you train, test, split it. Instead of calling the k nearest classifiers, you call the decision tree classifier. You do the fit, you call the predict. You do this. This is a step which I think was missing from here. Yeah. This is a step where you can calculate the scores. No, it was here. Yeah. And then you is just plotting the tree, how it looks like. This is how it made the decision. So these are the samples, these are the values. If the Gini index is this one, okay, maybe divided into two parts. One with, I'm not sure how it's dividing now, with value 31,000, one with 0,3737, then divide it again like this, and keep on going until it understands, okay, this is how the data can be split and classified into three parts. So this is how the scikit-learn library can be used. Now it's your turn to use scikit-learn library. I have given a Titanic ASK-learn IPyNB notebook. This is available in your exercise day 4 machine learning MLDL directory. Go there and run your Titanic sklearn. And to do that, you have to, just like I did, I started, if you are in an interactive node, you can do that. You can have your modules loaded on that node and then run your Jupyter there. And then because this is IPy notebook, you need a Jupyter server running there. And then go to that file and just run that file. I'll give, we have 10 minutes. So we have 10 minutes to do this. All right, welcome back. Now we'll start with PyTorch and TensorFlow. I hope some of you were able to run scikit-learn, that example. If not, we can come back to it if we have time later. Yep. So PyTorch and TensorFlow. Now we are in the deep learning section of this. Am I audible? Just checking.
Yes, we hear you.
Okay, thank you. So PyTorch and TensorFlow. As I said, this is primarily used for deep learning and they exploit GPUs well. I gave a little bit brief about the sort of history of TensorFlow and PyTorch. This is mostly developed. TensorFlow is developed by Google, PyTorch by Meta. By the way, TensorFlow is not anymore maintained by Google that much. They have given out the third parties to make their own versions of it. So Intel, for example, Microsoft, for example, have their own versions of TensorFlow nowadays. But when you download TensorFlow, you download the latest of what Google is still using. All right, so these have this is like a very vast library, PyTorch and TensorFlow, because deep learning, depending on which modality of data you're dealing with, is it text, is it images, videos, speech, they have their respective libraries. Language models have them, and graph neural nets have them. They're different ones. Then now large language models are there, so they have their own things in them. It's such a huge library, and maintaining these and like making sure that everyone is both academy and industry is able to use it in like same fashion is reproducibility gets difficult. So like I always recommend people to who are like using these libraries to always freeze their environments whenever they're using it, because let's say they are using some other libraries like transformers, Hugging Face, and they have backends in PyTorch and TensorFlow. Something gets updated in PyTorch TensorFlow, whereas Hugging Face doesn't do it, or the vice versa. It gets difficult. So there are like so many dependencies when it comes to when you start using these deep learning libraries. I always recommend to freeze your environments, the versions of the environments, that means. This is a very small example here just to do comparison, but in a sense, this won't justify the exact things which goes under PyTorch and TensorFlow. There's just so many things, but just to give you an example. So there is a package called PyTorch, by the way, called Torch in short, NN, which is neural net, and Optim, which is for optimizers. And of course, like here, I would expect everyone to understand what deep learning is, the nitty-gritties of it, to understand how to use them. But that's not possible, as I just saw, that no one knows machine learning, deep learning. So ask me questions if you have, like, okay, what is this? What is that? This is where neural nets are used, like to develop. So if you need to make a model using neural net, you use NN. If you need to optimize the parameters and the model, hyperparameter tune them, etc., Optim comes into play. Similarly, in TensorFlow, we have Keras as the backend of TensorFlow, as I was explaining. Layers is what will create the layers of the neural nets. And optimizers is again just like this one, having different kinds of optimizers to update the models and stuff. A very common thing which you will hear is tensor. TensorFlow has the word tensor in it. PyTorch uses tensor. And what is tensor? We already discussed, like in pandas, maybe NumPy, Numba, ND arrays. And when things get out of hand, when it's like multi-dimensional arrays, these are just called tensors in deep neural net terminology. So scalars, matrices, tensors, but in these two libraries, everything is a tensor. Except TensorFlow uses the word variable when it's a sort of a tensor which doesn't need to be updated. Okay, so first of all, tensors has a tendency. So this is a different class of like it's sort of an object, a class, which lets you these libraries have to like observe in case the model updates itself. And what can these be? Well, the weights of the models. If you have heard about weights and biases in neural nets, let me just give you an image here. So if this is a classic neural net with input, with 3 layers in between and with output, then these lines which are going are the weights. And these 1, 2, 3, well, it's okay, this, not this, but there'll be like biases in each of these neurons. So this is like closely depicting what a neuron is. So they have weights and biases. Biases won't change, but weights will change when the model updates itself. And this is what needs to be observed by the library when it's trying to update the model. And that's where tensors come into play, because tensors are these special classes which you can differentiate and observe. In TensorFlow, these are just called tensors, and you use requires grad equals true, which means observe this variable is going to change in future. It's a mutable object. Whereas if it was a false, then it's an immutable object which cannot change. TensorFlow has a different word for this. It's called a variable. And if it's immutable, then they call it constant, tf.constant. So this is a thing that you'll hear in both PyTorch and TensorFlow called tensors, torch tensor, tf.variable, and tf.constant. And I might touch upon why it requires differentiation or gradients later. Automatic differentiation. So other examples are differences are if you want to do differentiation, which neural nets do a lot of them. Then PyTorch has this inbuilt by just calling dot backward, and it will start calculating the differentiation, doing the differentiation. And why it calls it backwards is because if left to right is like going from input to output, then right to left is like changing the variables, which are the tensors here, the weights. In order to understand the input, you like make a prediction, you see the output, you see, okay, the prediction and the ground truth or the output was different. So let me just update my model in such a way that it understands the input better. And in order to do that, it goes like a backward pass, which is like if you have seen differentiation and like those long chain rules of differentiation, that chain rule itself requires a backward movement sort of way. So that's why it's like a backward word. Whereas TensorFlow uses tf.gradient tape class to do this same thing. So it observes whatever goes on into this under the width, this as this, and then it updates the gradients. Example of a neural net can be like simple linear layer. This is a linear layer. This is a 3-layered neural net. But you can change that, of course. So you can add layers after layers and do whatever with that. In PyTorch terminology, it's called just a linear layer. In TensorFlow, it's called dense. You give the shape. Like if it's, in this case, it's like a 4x3. It can be anything else. So you give a shape of the layers. And then finally, the optimizers, which will optimize the model, the parameters of the model that is given the input and the output. So things like stochastic gradient descent is a algorithm which is used as an optimizer to do that. It's a very lame sort of optimizer nowadays. There are other ones used. Adam, one of the most used ones in large language models as well. So this optim library is used for that. And the backward pass again, like to compute gradients. To clear the gradients, there is a special function in PyTorch called zero-grad, which will remove the gradients, which are the intermediate calculations. It will remove them. And step is just updating the weights of the gradients. So it calculates the gradients. For example, in this case, if it's trying to calculate the gradient here, it says, okay, what is the change of the final output with respect to the change of this weight? So differentiation of this by this and things like that. So, and it goes back like that, differentiation of this by this. So it's trying to update. So that's what PyTorch uses .step, whereas TensorFlow does that automatically. there is no step in it, but just apply gradients and it will just apply the gradients, which will like update the weights automatically. And this is just a very simple way of comparing them. But now we will try to like run these files and see if we can make them run on GPU if you have an interactive node on GPU, otherwise CPU. I see Pedro has a question. Yes, Pedro.
Yes. Do you use some debugging tool to know, for instance, the values of the variables that during the runtime, and to see if there is any problem during the running time?
Yeah, so when neural nets are big, doesn't make sense to like look at the values because you can't make sense of those values anyway. But things like if it's like a infinite value or it's somewhere there was a divide by zero happening there, and because of that there was not a number NaN happening somewhere in the values. For those things, then you can you have the tensor variable available. I think there are functions around tensor variable which can check whether there was, like in pandas we have isnan, isnull, things like that. You can check those things. But actually looking at the values won't make much of a sense. You can, of course, like in this case, print the output, which is the intermediate output. So you read one layer and you output that layer's output, which by the way are called activations, and see them. But then again, you do most of the time you won't know what you're looking at because you're looking at a model in between a run where it was not even able to understand the data completely, right? But then there are, because PyTorch and TensorFlow is like very well used, there are ways to understand the neural networks internals, and there are external libraries to do those things. And I think Meta has some, Microsoft has some, their own libraries to do that. I'm thinking of, it all comes under explainable AI, by the way. So if you find explainable AI libraries, the whole purpose is to understand what's going into the internals of the neural nets. And people have made dashboards out of this and things like that, where you can just upload your model and see the weights and things. Otherwise, these models are so big, like GBs and GBs. But you can search external libraries for such work.
Okay. Yeah, thank you.
Okay, so we have a PyTorch example and a TensorFlow example. I encouraged you to run, because you already have an interactive node and the environment's ready, to just run these PyTorch and TensorFlow examples. Just do one of these, it'll be enough. This particular one, which is called fashion MNIST image classification, requires you to submit a bash script, and the bash script is given here. So start up your interactive node, which should already be started. If you are, let's say, on HPC2N, give this bash script, change the source, which is your own environment where your TensorFlow is, if you're submitting TensorFlow or the other one. And then, of course, edit the path to this fashion MNIST, which in this case is, this is also uploaded in the exercise folder. So you'll find that in the ML folder. Let me get it bigger. Oh, this is not, it's too small. Under ML folder, you will find PyTorch MNIST and TF, which is TensorFlow MNIST. So you can run this and this, and it requires and it requires the data sets, which are also given in the datasets folder. So try running these files and also check whether the training data and the test data file paths are correct. It would require you to enter the full path of the dataset. So let me show you this example, which I ran some time ago. So same file, only thing is I gave the full path of the PyTorch folder for this PyTorch MNIST. And my Slurm script looks exactly the same like that, except that my source is the name of the environment and the path to my PyTorch MNIST.
Which conda, am I correct?
Yeah, so do that, and then you'll know that your Python, your pip, and everything is on this correct place. Look here. Look at the leftmost part.
Thank you, Jayant.
So when you do that, I have submitted mine, and I can show you how the outputs will look like. This is the Slurm output. So I think this is PyTorch. It will just look like this. And by the way, this is on Tetralith. So it will show you from 60,000 steps. After every few steps, it says, okay, this was a loss, this was a loss, this was a loss. So it's trying to decrease the loss, as you see, 0.2, 0.8, 0.5, 0.7. It increases sometimes when it decreases. And then there are like epochs, which means use the same data set again and again and again. That's like one epoch if you use it once, and learn through the data set. And by the time it ends, which is after 10 epochs, the accuracy is 87.6, and it predicts something. It started with 84.5 accuracy, and by the time it was done, it ended up at 87.6 accuracy. So MNIST is another, fashion MNIST is another like sort of a famous data set to play with. It's basically a lot of images of clothes, and you need to predict whether this is a sweater, this is a shoe, this is that. So you need to, you're using a neural net to train. You classify whether this image is what. Another important data set is called MNIST, which is basically just handwritten digits. And then you classify whether this is 4, 1, 0, 7, 8, 0 to 9, basically. So there are 10 classes. Fashion MNIST is just a rip-off of MNIST data set made in the lately. So we are 15 minutes away. So I'm going to start with the tips and tricks. And maybe hopefully we reach to the exercises, and you can run interactively one of these notebooks, or you can just run these notebooks interactively anyway, because these will be like very quick if you have already interactive session running on. So one of the interactive sessions, which is this exercise, which is this exercise, which is a miscellaneous example. I'm running this interactively here, and basically there's nothing to show here, but just to show that I was running on a GPU node, and it did its prediction as it was supposed to. And this is using a PyTorch. This is a TensorFlow example, and using Jupyter kernel, using VS Code. I won't be, of course, going through the code here, but it basically has a small neural net, and that neural net is trying to predict something. It's just it's an ionosphere data set. Okay, so to the tips and tricks, which is basically what I see usually people making mistakes is, first of all, is not understanding what kind of data types they're dealing with. This also happens in simple machine learning cases where they just take the data and start playing with it, but they forget to even understand the data type. And why is this important is because when the models grow, especially like large language models, which are in GBs, knowing what kind of data type you're dealing with is important. Otherwise, you won't be having enough hardware to even run your models on, which is GPUs basically. So the models are very specifically tuned for one kind of data type, especially these large language models. So if you understand your data type way earlier, it's better. This reduces the memory usage of your models and the training time it requires to train your models by like a large amount. Then versioning, as I was mentioning, that PyTorch and TensorFlow are like huge libraries, and with that, when you start working with them, you'll find conflicts. It's always good to freeze your dependencies so that in future, when there is a new version coming out and some other version is not updated, your code is not getting harassed. So always document them, document the versions, freeze your dependencies. And if you're like very finicky about, okay, there are so many dependencies that you're just populating my home environment. So try to be like careful with where your environments are. Right now, we are just running without even taking care of where the environments are being stored. If you're using Conda, then some of it will go into your home folder, some of it will go into some other place. So be very wary of where your environments are getting stored, because that will clog your deplete your quota, memory quota, or storage quota. With machine learning and deep learning, always like start small, which means if you have to train a lot, start with like a small data set, small batches of that data set, and then slowly build upon that. Start adding more, try to scale it more, because bottleneck will always be for everyone the hardware, which is GPUs. And like training a very simple model can take days, so if not hours. So it's important to like start always small so that you know that at least everything is working from end to end. A lot of people say that because they start like a very big data set, big batches of data set, they always go through out of memory errors, OOM errors on GPUs. IO operations is another thing, which is one is of course the memory. The other part is the IO operations, and this is usually not the problem. But sometimes it happens that you have so many data, so like very small data sets and very small data in like chunks, that you finish up your quota for like number of files. So batch them together in a way that you have already like ready for like loading your data set into the model, and you are also not finishing up your number of files. Using specific machine learning data formats like HDF5 that you learned yesterday can also help, because it first reduces the size of the data sets, and also it batches them nicely, and they're also very quick to load onto the models. Storage management is like a very general statement again. So always look at how much quota you have, how much data you have. And if it's not like very small, or if it's like a not very large number of files, So always take that into consideration when you're learning or like training your models. In fact, like when you're training your models will also be saved. Every checkpoint they will be saved. You would want to save them. So that will also deplete your storage quota very quickly because they are like in GBs. So that is there. GPU memory management is something which is when you start getting advanced and you start understanding, okay, I have CPU as well as GPU on my node. How do I profile them? How do I see uh, to do good memory management with them or understand how is my model even loaded there? This is where simple tools like HTOP is available in some HPCs. Of course, look at the cores which are being utilized. If you're using PyTorch, then you can go to this link and upload your model there, and it gives a breakdown of how your model looks like. So these are some example of how model was trained. So it will show it at every iteration of the model training, it loaded and then it removed, it loaded and then it removed things. And the memory is on the y-axis and the time is on the x-axis. So you see that it's increasing, the GPU allocation is decreasing over time. So this helps understanding how your model is improving or like clogging up the memory CUDA. So NVIDIA Insight is something available on Alvis. Otherwise, TensorBoard is available, for example, on UPPMAX. You can do that there, or just upload your PyTorch files to this link and see. This will let you avoid out-of-memory errors if you understand your model and the GPU memory properly. So if you're using T4, if you're using A100s, if you're using L40S, these have different memory requirements. They have different CUDA capabilities. So understanding how big of a model you have and how big of a data you have and how much is available on this GPU helps. I'm not going through this. Job monitoring is important. A lot of times it happens that, not a lot of times, few times it happens that someone has just utilized a lot of IO operations on the node and the node is crashing or things like that. So admins have to come in and they have to sometimes kill the jobs. And if your jobs were like training a model for a very long time, it might be bad for you, right? So always log everything, do checkpoints, save the models in between the training so that whenever something bad happens, you already have and you can start from there. And finally, like always, like try to improve the performance by using these GPU tools that I mentioned in this line and use appropriate sizes of the data sets in accordance with what hardware you're using so that your GPU runs well for your model. So yes, and just monitor resource usage, for which means like you were already looking the GPU, HTOP or NVIDIA SMIs to look at, okay, these many cores were being used at the time, or with NVIDIA SME, you can see this many GB of GPU is being utilized. So that, okay, so we are actually unfortunately out of time. We are taking 15 minutes break now. I'm available right now. If you have, if you're doing any of the exercises or running anything, or if you have any other questions. After the break, we'll have Anders Hurst joining us, and we'll be learning about some of the techniques to do dimensionality reduction. If you remember, we slightly touched upon that in sklearn, where I was saying that one of the components is transformers and there is a PCA, which is for dimensionality reduction. But he'll be talking more about it. And we'll also be using some files to, we will be running a file for exercise. The same file can be found in the under day 4 dimensionality reduction folder. It's called dim-red IPyNB. And you can run this file with one of your TensorFlow environments that you created. So we'll be back in 15 minutes. Thank you.